sometimes when we have curves, we're interested in knowing the length of the curve, okay? But the problem is, well, curves are curvy, so it's not exactly that easy to go right ahead and measure. So what we do is we zoom in on the curve until we see a piece of the curve that looks basically linear, basically straight, okay? And then we say, okay, I know how to measure a straight line. How do we do it? We say, well, if you're the curve, I'm going to zoom in and find a line find a piece of the curve that's almost straight, okay? And then I can take that straight line and I can measure its length by applying the Pythagorean theorem, right? I can say, well, you went 3 units right, 4 units up, well, you're 5 units long, okay? So that's going to be the sort of the methodology that we use to measure the whole curve. We're going to break it up into little pieces, and each piece is going to be square root of dx squared plus dy squared long, right? Pythagorean theorem. But then we do a little bit of algebra, and we say, well, okay, I can introduce this factor of dx squared over dx squared. I can just do that because that's 1. So I can multiply the second one, and the reason we do that is because now we have another name for this expression. It's the derivative of y with respect to x squared, okay? So we can say, all right, well, this is the derivative of y with respect to x squared, and now I can factor out the dx squared, and I'm going to end up with dx squared times 1 plus the derivative of y with respect to x squared, okay? So now I can take out the dx squared, and I'll end up with this expression. Pretty simple, right? So now I don't need to know for each sort of line how far did I go in x, how far did I go in y. I know how far I went in x, it's dx, and I can calculate, since I know the function, and I can calculate how far I went in y in terms of x. Okay, so that's the big idea. You say, okay, well, I went this far in x, how far did I go in y? Well, it's this guy, okay? So we can use that to figure out what ds is. And how do we find the length of s? Well, you just add up all the ds's, okay? So we just integrate this expression that's effectively equivalent to ds over our sort of our interval. But notice something. Notice that this choice of introducing the dx squared over dx squared was sort of arbitrary. I could have done it to the other term, right? I said I have a dx and a dy. They're speaking different languages. I'm going to introduce this dx squared over dx squared to make them speak the same language, dx. What I could have done is said, well, I'm going to make dx speak the language of dy, which I did here. I introduced a factor of dy over dy, or dy squared over dy squared, and then said, okay, if I know the rate of change of x with respect to y, then I can do the same thing, except sort of the opposite. Here I said 1 plus derivative of y with respect to x. Here I'm saying the derivative of x with respect to y. Okay? And my integral is going to be in terms of y. That's the only thing. The approaches are exactly the same. We're gonna end up at the same expression, except here everything's in terms of x. So the derivative of the function is in terms of x, and so is the integral. And here the derivative of the function is with respect to y, and so is the integral. So let's go ahead and do an example to see how this plays out. So we have y squared is equal to x to the third. So let's go ahead and graph it really quickly, just so we have a visual for what's going on. Well, y squared equals x to the third. I'm not exactly sure what that's going to look like, x to the 3 over 2. But what I do know is that as x approaches infinity on the right side, this thing is going to blow up, right? Nothing to bound it. It's just going to go to infinity. And in fact, I know another thing. Since it's being divided by 2, so it's inside a square root. This is the same thing as square root of x to the third, right? I can't have x be negative, because if it's x is negative, this thing becomes imaginary. So I know nothing from the y-axis left is going to happen. Nothing happening there. So I'm just going to, and I know it's going to come from the origin. So it's going to look something like this if I were to guess. I'm not exactly sure. I just know it's going to grow faster than a linear and not quite as fast as a quadratic. Okay? So I'm interested from 1 to 4. So let's go ahead and actually do it. So it's from 1 to 4, and then the expression, remember, 1 plus the derivative squared dx. And then what's the derivative? Well, the function is x to the 3 halves, so the derivative is 3 halves x to the 1 half, right? But don't forget, you're squaring this whole thing and then dx. Okay? So now we're going to actually go ahead and do the square, and I'm going to replace the square root with parentheses raised to the half power. So we're going 1 to 4, saying 1 plus, now 3 halves squared is just 9 over 16. I'm sorry, it's 2, 9 over 4. And then x is going to just get first power, and then we're raising it to the half power, or to the 1 half. Okay? So now we got this guy. What do we do? What do we do? Well, we have 1 plus 9/4 x. So we just do a u sub. You don't have to do it. You could do it in your head, but I'm not that smart, so I'm going to go ahead and do a u sub. My du is just going to be 9/4 dx. So dx is going to be 4/9 du. And again, this last step isn't required, but I usually do it anyway. So now I got to do my bounds, right? I applied a u sub. I got to redo my bounds. So when I plug 1 into this thing, I get 9/4 plus 1, or 13 over 4. When I plug 4 into this thing, I get 10. Okay, so now this expression is simplified. It's just u to the 1 half, but we have the 4/9 out front, du. Okay, so we can integrate this pretty easily. We can say u to the 1 half, its antiderivative is u to the 3 halves times 2/3. So I'm going to write the 2/3, then say u to the 3 halves evaluated at 13/4 and 10. So now I'm going to have an 8 over 27. I don't think this is going to be very nice. Then we have 10 to the 3 halves. Well, that's just square root of 1,000. I'm sure you can simplify this a little more, but I'm not going to. 13 over 4, well, the 2 comes out and then gets raised to the third, so it's 8. The 13, I'm just going to write 13 to the 3 halves. Okay, so that is going to be your answer. You could simplify, but I'm not going to. But as you can see, it's not hard. You just basically have to do the calculus right and setting it up. Sometimes you're going to have curves that may be parametric. If they're parametric, then use this definition, although you shouldn't really see a parametric in this section. But you could be asked to use this or this, depending on how your function is set up. If I gave you your function in terms of y, you shouldn't try to solve for y and write it in terms of x so that you can use this guy. Just go ahead and use this thing. It's exactly the same process. Okay, so there you have it. That's arc lengths.